Let me show you how to calculate rocket propulsion here. Now, the only sad thing about this lesson is that after this lesson, you will no longer be able to say, I'm not a rocket scientist, but, right? Okay, so some people like to, I mean, maybe you don't want to cross that threshold, right? Okay, you might want to consider whether you want to learn rocket science, right? Because after this point, technically speaking, you will be a rocket scientist, okay? So you might want to pause a little bit. Think about it. Do you really want to become a rocket scientist? Okay, are you still there? Are you still there? Okay, good enough. I'm going to show you. Okay, here's the notion is that rockets generate thrust. I'm just going to hit the right arrow here. Okay, rockets generate thrust. That's what this force is here, right? For some amount of time. T is they call it the burn time, right? They do it, and what they push off of is just the mass of the fuel that they burn pushed with some velocity, right? And ultimately these become force times time equals mass change in velocity problems, okay? So that's the short version of this, right? So the answer to the question, what do rockets push off of? They don't push off the ground. They actually just push off of the fuel that's getting pushed this way. It's Newton's third law. If you push fuel that way, then the rocket gets pushed that way. For every action, there's an equal and opposite reaction. And those things act on different objects, okay? So what we're going to do in class is we're going to do a version of, I'm going to go to the next slide here. You probably want to write this down. Yeah, okay. I'm going to do this in class. The question is, does one of these rockets have an advantage? Right? Do they push off the ground or do they push off of their fuel? If they push off the fuel, neither one has an advantage. If they're pushing off the ground, the one that has the ground has an advantage. This one, the ground's so far away, right? Okay, so we're going to actually do a demonstration in class about this. So look for that. We'll start off with that, right? So the question is, what do rockets push off of? Okay, so people always look at that, right? They think that barrier there is what the airplane pushes off of this. It's like, right? Do they really push off that? Is that what that's for? There's another picture of it, right? Okay, so let me just show you how to do one of these problems. They're not really very hard. It burns fuel at a rate of 1.2 kilograms per second. Now, we haven't seen kilograms per second yet. So here's how I'm going to deal with that. 1.2 kilograms per second means that when the time is 1 second, okay, the mass is going to be 1.2 kilograms. And it's as simple as that, right? Here's our velocity. That's our change in velocity, right? Is 1250, right? And then we just want to find the force, right? So this is what you do is you just set it up. Force times time is mass, change in velocity. And if they give you kilograms per second, put 1 second in for the time. Force is what we're trying to find, right? And that's 1.2 kilograms times, and then our change in velocity is 1250. Okay, so we are ready to go here. 1.2 times 1250. Then don't forget to divide by 1, right? Divided by 1, right? That's 1,500. The force is 1,500 newtons to that. Now, as you might suspect, there really is sort of a hidden formula here, right? Notice if you have kilograms per second, that time is always 1 second. It's 1.2 kilogram in 1 second. Right? So you actually can write it this way. Force equals mass over time. That becomes the fuel burn rate times, right? So basically the thrust of a rocket is its fuel burn rate times the exhaust velocity, okay? I don't want another formula, so I'm just going to stick with this guy. This is my friend. For rocket formulas, just make that 1 second, okay? So let's do another problem that's maybe a little more difficult. Okay, so it develops 12 newtons of thrust. That's our force, right? Force times, actually here I'm going to start over on this side. Force times time is mass change in velocity, because this guy has 2 parts, right? So the force is 12 newtons, and it does that in 1 second, right? It burns some mass of fuel, right? So if you want to find the burn rate, make the time 1 second, and then 718 is our delta V, right? Meters per second. These are newtons. Right, okay, so then I just go 12 divided by 718, 12 times 1 divided by 718 rather, right? And the mass is, in 1 second, the mass is 0.0167 kilograms, right? So the mass burn rate is that many kilograms per second, right? Sometimes mass burn rate, you talk about m dot, right? M dot just means the rate, the time rate of it, right? I don't generally do that, but there it is, right? Now, the second part of this is what's the acceleration of the rocket, right? So let's draw a good rocket here, right? And the rocket, we talk about the initial acceleration, and that's because rockets, a large part of their mass is their fuel, and so initially they're very heavy. So there's a lot of gravity and there's a lot of inertia, and they don't accelerate quickly. But at the end, right before they run out of fuel, okay, they've still got a tremendous amount of thrust, and they don't have much mass, right? So the acceleration actually, you know, if you draw a graph of acceleration versus time for a rocket, it's like boom, like that, right? In fact, in the Apollo missions, they actually took the rockets and took them offline. They had, like, I think in the first stage, 5 engines, and they take one of them strategically offline. Otherwise, they would create too many G's for the poor astronauts, right? Okay, so let's do this one. There's a force upward. That's going to be 12 newtons, right? The force down is going to be the force of gravity, and that's going to be mg, right? So 0.238 kilograms, right? Times 9.81. Okay. 0.238 times 9.81. That's 2.33478 newtons. Right now we're all set. We can set up our F equals ma. So 12 newtons up minus 2.33478 newtons down, right, equals 0.238 times a. Okay, so divided by 0.238, and I get that the acceleration is 40.6 meters per second squared. That's the initial acceleration. The final acceleration would be more than that, because not only would there be less of this, but there'd also be less of that, right? And both of those getting smaller would make it a bigger acceleration. Alrighty. If you want to learn more, just go to the Wikipedia page for Saturn V. Saturn, that's an N, V. Go to the Saturn V thing on Wikipedia, and they show you the force, the acceleration curve, and talk about what they did.